Hello everyone, welcome to today's webinar on autonomous geometry processing using machine learning. I am Sandeep and with my colleague Subhranshu, we are going to walk through the technology we have developed for geometry processing using machine learning techniques. Let me quickly introduce you the speakers of today's webinar. I'm Sandeep, I'm CEO of Citec. I've been working with Autodesk and many other OEMs on CAD, CFD, CAE application development. We ourselves has developed a simulation of platform, which again helps designer to create autonomous applications. My co-speaker for today's webinar will be Subhranshu Manji. He is head of AI consulting at CCTech. Subhranshu comes from mechanical engineering background. He has worked with various domains such as AI, CFD, computational geometry, genetic algorithms, and evolutionary algorithms. So he will be also taking you through the more detailed part of this webinar. I will be giving the introduction. So let's get started. We will be covering why you need autonomous application to process the geometry, how the data is exploding in the field of geometry. We will be also going through the what sort of mesh representations we are using. We will be going through the mesh segmentation problem and the sub problem that we try to solve for a 3D object detection. As we know, today there is so much of geometry data available because of the different 3D applications that are available to each of us. There is a geometry data coming from CAD application. There's a geometry data coming from the different sensors. The geometry data is getting created through scanning devices. So to process all this data, we need to have a better system. All of us are saving this different geometry data. Those data is in a trillions of bytes, but we don't have enough human resources to process them. So what we need is an intelligent system, AI-driven system, what we are calling as an autonomous geometry processing. So let's try to understand this problem in more detail. Let's say there is one design firm, a product company, which designs a product. So when it designs a product, it needs to get communicated for the plants, it needs to get communicated for the logistic, it needs to get communicated to the manufacturing, it needs to get communicated to the end sales and marketing team. For all of this, typically the data at the start is in a format of either building information model in a construction industry or in a CAD model for a mechanical, aerospace, chemical industries. This data, when it reaches to in a plants, it will be either in OBJ or STL file format. When it reaches to logistic, it will be again in the format of PDF or STL document where you don't want to share too much of detail. When it goes to the sales and marketing, it's in a much more lighter format like JT format or 3ds file format. Now, all this format have created a different representation of the same data. So the source format, as I said, is a CAD and BIM, and at the end, the formats are typically OBJ and STL. Why all these people converts into OBJ or STL is multiple reasons. One is intellectual property right protection. You don't want to hand over your parametric file data information to the STL or to the end user. So OBJ and STL gives a limited information about a model. But this itself created a bigger problem that now that OBJ and STL doesn't have parametric information. OBJ and STL, one more advantage with them is that they are very easy to read. You can get a free viewer. So you don't need the expensive CAD or BIM application. So if you look at this in a very broad context, today you will have, if it's a trillion bytes of data of geometry that you have, 95% of that data is in a mesh format. Only 5% of the original parametric file format are available. And when we try to apply a machine learning application for this data, you cannot use this data for OBJ or STL file because this data doesn't have any uh, parameters in it, and without parameters you cannot use it for many of the purposes. So this is the one of the thing that all of us face as a challenge. So another thing is this format, CAD and beams are at a very few people and few I would say custodian of data only has this file formats. So we need to unlock that so that everyone can use this data and make a meaningful application. So solution for this has been is kind of in a form of reverse engineering. So what um, companies do is that they employ certain reverse engineering organization where they put thousands of engineers to take a STL file and then try to create a CAD file out of it. So even if it's a data from their own organization could be because they have lost the CAD file format, they have to again go through the STL to CAD conversion. And since STL is very prevalent, the STL files have written their life, but the CAD files are not able to retain that. The data also comes from scanning devices. In that case, also the data is in a point cloud or mesh file format. So and so if you have point cloud data and you want to create a building information model to map how the progress of building is, you again need to do this manually. So in both the situation, what you need is automated system. So this is not a problem only for CAD or mechanical industry or AEC industry. This is a problem prevalent in other industries also. You might see there are a lot of Word and Excel file are being trapped into PDF files. The original Word and Excel files are lost. And if you want to now read those data from PDF, it's not that easy. So to solve this problem of reading the data from PDF and then recreating Excel and Word, these three main companies have taken this as a to build a web services. So there is a now services by Amazon, there is a service from Microsoft and Google to read the PDF file and then convert them into Word and Excel. So this is a now very well developed technology that is available for you to use. We ourselves have been using this for various industry where they have a raw data in the PDF format, and we are helping them to convert that PDF data into Excel. The technology has even progressed. If you have a data in images, so if you have an images of a document, because many of them people have printed them and then they have scanned them, so they have that data, and we are also able to convert that scan image data back to original Word, back to original Excel. And then once you have that original parametric data, you can use it for further processing, like for AI and ML application building. So AI is helping you to build even more data for AI. So to solve the problem for a mesh format and or the geometry data in a OBJ or STL to convert into a CAD or BIM, a parametric format, we decided to do some research. So we worked on this problem, created the AI and ML solution, which has now become a kind of a technology offering for anyone to use. That's what we're calling as autonomous geometry processing. We have done two things here. We have automated the workflow and we have also added the intelligence. So automation plus intelligence is what we're calling as autonomous in this context. So uh, with this new web service that we have built, what you can do is you can submit your OBJ or STL file, and at the end what you get is a segmented surface patches which can be used to create a CAD model or a BIM model. That's the this service in a very simple term. So let me go back again why and where that data is coming from. So there are STL file format, there's a OBJ file format. As I said, there's a lot of point cloud data which is coming from the scanning devices, and with now augmented reality and other devices, again there is a huge amount of data that is being put into the cloud. So geometry wise nowadays you have a really huge amount of data. The question is how do you process that data and create a reusable kind of format. So let's see how do we apply this AI to geometrical data? Because what you see is that if you go through AI and machine learning algorithm, you will find a lot of algorithm to process images, videos, text, and these are the very well developed technologies. But you will find very less amount of material about how do you apply this data for geometrical data. So we need to understand this part in a more detail. Before I go and jump into that, because we are going to talk about a machine learning, let me explain what machine learning means. There are few who may not know what machine learning means. So if we look at programming in a traditional programming, where what we do is we give a data as an input and program as an input to the computer. So computer processes that data using our program and creates an output. That is the way we basically create any programs, and that has helped us to come to this way. Now we have so much of data that we can ask computer, take this data, take one more data, what we call as a label data, or we call as output data, and can you create a program out of it? And machine learning is the branch which helps you to create that program, and that's what we call as a machine learning model. So this is the what I would say 40,000 feet view of what machine learning is. It's able to create programs just based on the two data. One is the input data and one another is the output level data. Based on these two, it creates a program. So in autonomous geometry processing, how we have went about this is basically we have a tessellated mesh, and we created that from the feature rich CAD model. So we have basically uh, used this raw mesh data, like you see a bitmap image where there are only pixels, and then you have a SVG image which is a vector image, kind of rich data. So that sort of thing is what we are able to do. We give it a mesh data and able to create a segmented data which is able to identify which are the surfaces and information. Once you have that, you can do a lot more meaningful use of this mesh data. So let me go into more detail why this is challenging. So if you look at the image data, uh, in image, one thing is that it is very structured. So you have a certain pixel, you have a length by width pixel, and then you uh, take that set of data and put into machine learning, which able to segment you to identify each of the objects. So you give this image data, ask it to identify whether it's a cat or dog and things. It can even nowadays identify the backgrounds. So this kind of segmentation part is what you can do with the image data. Now, when we try to extend this to the mesh, there are some interesting things start to happen. As I said, in image, the data is very structured. In mesh, the data is unstructured. So if you have a one vertex, you are not sure this vertex is shared by how many triangles. It can be shared by 3 triangle, 4 triangle, 5 triangle. It can be even shared by hundreds of triangles. If you look at an example of a cone, apex of a cone, there are hundreds of triangles that are connected to the apex of a cone. So this is one of the problems that you see. The another thing is that in image data, there is a uh, you can go from, let's say, 512 by 512 to 256 by 256. You can go to 128 by 128. So there is also a structuredness between that connected. So it's not just an order of L by W, like where you know the neighborhood, but it is also possible to create a layer in that image data. That's very difficult to do with a unstructured mesh data. So how does industry look at this? For to explain this in more, I would now ask my colleague Subhranshu to take you through the next set of presentation. Thank you.
Okay, thank you, Sandeep. And once again, hello to everyone. So, I'll be taking you through the deeper mathematics that is involved in the machine learning model that we have created for the autonomous geometry processing application. So, let's begin with this. What the world is experimenting today. So, nowadays a lot of research is being going on to a particular use case, that is to to perform segmentation of 3D geometries. So basically what we can say is detecting body parts, like in this example, and also extending it to objects and detecting the pieces that are connected together in order to create this uh, objects. So such kind of use cases are being highly researched these days. Uh, Other examples involve like detecting the pieces of the geometry which are separated from each other, like the chairs and tables and other um, humans and everything. So such kind of use cases are being highly researched today. So one typical trend that you will observe is all of this is addressed from the volumetric point of view. I mean, the approach to these solutions are from the volumetric point of view. Like pixels are for images, 3D cubes that are voxels are for 3D geometries. So here this example also shows that how these volumes have been created, and based on these voxels, the voxels are grouped together, or the volumetric cells are grouped together and labeled as one component and the other component, and so on. So basically the success of neural networks which happened for the image processing is being extended into the 3D geometry world. So that's the typical approach that is being taken these days pretty widely. Here is another example of the same extension of image processing into the 3D geometry area. So what happens here is, in this approach, 360-degree images have been taken of a 3D geometry inside a 3D viewer. So these are the images that has been taken, and these images go into a CNN network, which at the end classifies as this object looks like a chair. So it's pretty similar to what image processing does. So even though it's a 3D geometry, you scaled it down into a 2D geometry and then detect the classes. So for classification purpose, this approach will be a good approach, right? But the approaches that we discussed are mostly extension of the CNN networks, which are very popular for image processing, are being extended into the third dimension. Alright, let's move on to our research work and understand how we have addressed it. So I'll go step by step from here. First and foremost comes the dataset generation. So to begin with, we started collecting almost 1,000 or more than 1,000 CAD models. Those are all mechanical parts basically in the format STL and OBJ format. Here are a few statistics of the dataset we generated. From roughly 1,500 CAD files, we received around 19 million triangles, and you can see the distribution here at the top section. So typically in mechanical objects, this is what type of distribution that we get, and our objective is to classify these surfaces, right? So here are some more insights, like the dataset size was around 10 GB, and the most interesting part is we were able to come up with 100 or 100 plus features for each triangle. However, with ML model creation journey, these features will keep on filtering out, and only the most significant ones will eventually continue. So even though it looks like 100 features for a single triangle is too much, what sort of properties we could have collected for those 100 triangles, right? 100 features, right? So that will not go all into ML model, of course, because some features might be really important for ML model to get trained on, and some might not be. So such filtering operations will be happening before we finally go ahead and train the model. Alright, so let's deep dive and understand what could be the features we can come up with for such a small thing like a triangle in MS data, and also we'll look at its challenges. So let's take an example of a bottle design. So this STL file contains lots of triangles that form the shape of this bottle, and this bottle is horizontally placed. Now let's focus on the highlighted triangle. This data below represents the coordinates of the vertices of this triangle. If I directly pass these coordinates into ML model and train it saying that the triangle belongs to the cylindrical surface, I'm sure it's not going to work because the moment I translate or move the bottle in a little or say rotate it, the coordinates of the same triangle is going to change, right? And now the ML model will see a new set of data, and when we ask the model to tell me the surface type it belongs to, this would be a little difficult job for the model to tell, right? So the data is changing, and the ML model has to learn that these two different data eventually belongs to the same triangle and the same surface. So basically the point that I'm making is the coordinates of the triangles is highly specific to this particular CAD file and this particular orientation of this particular triangle, right? So we need to make the information as generic in nature as possible. The information should be independent of the location and orientation of the triangle. So that's the data preparation work that needs to be done. So let me take a pause here and refresh the fundamentals of machine learning one time again here. As we know, machine learning needs two things. One is the feature, that is the input to the model, and the target, that is the output to the model. So that the model basically needs to train on. Okay, so in the target area, we know that our problem statement is like we need to classify each triangle into its corresponding shape or its corresponding curvature it belongs to. Like a triangle can be classified either into a planar surface or a cylindrical surface or a spherical one or a torus one and something like that. So targets are simple, it's just classes, but what we need to feed into the machine learning model in order to classify it or learn that it belongs to this class or that class. So that's the important aspect we are looking here. So we just learned some time back that coordinates are not the right input to be given to the triangle, to the machine learning model. So definitely it means that we need to focus on the intrinsic properties of the triangle in the mesh data, right? So as we see in the bottle example, if the bottle is rotated, then the exact coordinate of the mesh data was changing, right? So for this, we are more focusing on properties like angle between normals between the two adjacent triangles. So a curved surface will have angle more than 0. A planar surface will have two adjacent triangles with 0 normal, 0 angle between their normals, and so on. So also getting a sense of how small the curvature is or how larger the curvature is. So such kind of information will not change when the change in the location and orientation of the body, right? So again, edge length or say area of the triangle, area ratio of the triangle, ratio of the edge lengths, perimeter of the triangle, such type of things we can think of, right? So those type of properties we can keep looking for in a triangle and keep enriching the data set by such properties. So like this we were able to come up with hundreds of properties. That's a good start point, isn't it? Now we'll look at another feature, that is the we are naming it as geometry illumination. What it does is what we do here is if we look at the geometry from a specific angle and imagine throwing light towards that geometry from that angle. So when light is being projected to the geometry, the curvature and the shape of the triangulation or the mesh data or the geometrical shape will eliminate in a different way when we change the light source orientation of the light source. So that's what is happening here in this animation also. You can see that right two images which is showing the same geometry with different numbers or numerical data represented in the form of colors. You can see the numbers are changing. That is, those are changing because the direction from which the illumination is happening is different. So this is another feature which the ML model will definitely take advantage in predicting the triangle, whether the triangle belongs to a cylindrical surface or a spherical one or a torus one. Such kind of those predictions, this will be a really important feature. Then we also did some engineering or derived feature type of thing. What we do here is we take the primary features and then we take we do some apply some operations onto it and make some derived features, which will be definitely adding or helping the ML model to train on. So here in this example we are showing about aspect ratio, which is the length of the minimum side versus the length of the maximum side. So it's a ratio between the smallest side and the largest side of a triangle. So this is a pretty straightforward slide. It talks about how machine learning data needs to be normalized before sending it for training. So the ranges were different, as we can see in the raw data, which we normalized it to 0 to 1. That's all. That's about the slide. Let me move to the next slide. So topology embedding is the next topic that we will talk about. This is our innovation that we did in this ML model. The ML models usually, as we know, are to be designed for the particular use case, and the architecture has to be designed accordingly. So we also did some engineering on this, and this is what we came up with. When we say topology, we all know that topology consists of vertices and how they are connected to edges, and then how edges and vertices together create these triangles. So in tessellation, mostly we deal with these things, and these are all connected to each other, right? So for prediction purpose, we should also take advantage of the topology which is already connected in the real domain, the geometrical domain, and leverage that for ML predictions. So we also created such kind of a architecture where the branches were different, and one branch was focusing on the vertices, then the other branch was focusing on the edges and vertices together, and then all of these two were again merging into the test triangles, and hence we were taking advantage of all three of these information together and not separately, right? So that's what we are calling as mesh topology embedding. This is a diagrammatic representation of how mesh topology embedding happens. So you have vertex level predictors at the bottom, and then the information then gets feed into the edge predictors, and then the edge prediction then goes to, along with the vertex prediction, they go to triangle prediction, and that's how the results come up. The next step is about doing some data visualization in order to enrich the data, get some deeper insights before processing them and feeding them into the training process. So in the visualizations, we get to see the first thing that we do is we study the covariance matrix, and that's what helps us to recognize which feature is highly oriented and could be of real importance to us. So that's how we are presenting two features against each other and looking at the how they are aligned to each other, and we have shown that there are two highlighted visuals which give some insights about how highly correlated to each other. Then there are other such visualizations that needs to be done in any machine learning use case, where you can after getting these insights, you can take better decisions about the data. Then the next step involves a feature importance study. So there are libraries which help us to do that. What we do is, by running these packages and conducting the studies, we get to get a sense of which feature or which property is impacting the most on the results. So that way we are able to reduce the features which are not really significant, and reduce the data size, and also enrich the data by only keeping the highly correlated features which has potential to train the model strongly. Alright, the next is training and validation splits. This is an important concept, but pretty simple. So what we have with us is many triangles from many geometries. So that comprises of a very big data, and this data needs to be now split into 3 parts. So the larger chunk of the data will be going for the training purpose. The ML model will also consume the validation data together with the training data in order to train it on a more generic fashion and not get overtrained for the training data set only. That's why validation data is also important. And then comes the last part of the data set, that is the test data. This data will be never sent to the ML model for training purposes. So once the model is ready, we will send the test data and just check the accuracy of the model. So this data is, we call this data as unseen data. So the model has never seen this data. This is totally unseen data. And if this accuracy on this data is coming to be good, then we can confidently say that the model is getting trained well. And if the results are not good, then we go back and tune the model parameters. Then we rerun the training process, and the new model that is now created will again be tested for the test data. So this cycle keeps on going until we get a good model. So we need to take advantage of the latest cloud technologies which have really good GPU support. The dataset that we are talking here is of it's really huge. We have lots of geometries, and then these geometries have millions of triangles. So the dataset size is really huge, and we cannot run it on our local laptops or desktop computers with just single GPU cards. So we need to run them on the HPC servers in the cloud. So we have been using AWS for this purpose, and we consume 4 to 8 Tesla cards, and with lots of configuration that you can see here. Those kinds of instances are needed in order to train this huge data set. So once the training is done, the next thing to do is analyze the results and the reports of the training to identify whether the training went well or not, right? So confusion matrix helps us to do such kind of analysis. Here in our use case, we had a classifier type of ML model getting trained. So confusion matrix is a very good tool for that. Like you can see, the performance of the model is presented here. So for a case of plane, which a true plane got detected as plane for 92% of the times, and 2% of the planes were getting predicted as torus, whereas 4% of torus were getting predicted as plane. So very interesting insights here. You can see planes are getting predicted as torus for 2% of the whole data set, whereas the torus 4% of the whole torus data set was getting predicted as plane. So those kinds of insights we get to see. Now we know that planes are better off in this model. We need to work a little bit on the torus detection, right? All right. So that was a lot of machine learning and mathematics connected to it. Now let's go ahead and touch the next segment of our webinar, that is how did we create it. So machine learning being the core of the application, but it still needs a app around it to be created in order to make it usable, right? So Autodesk Forge was used as the geometry processor or the front of the application. So here we are able to upload models into the Autodesk Forge viewer, process that data, and then finally run the ML model and get the predictions done. And again, at the end, we will display the results. So all of this was done through Autodesk Forge library. And for making the web application, we decided to go with serverless technology, which helps us with reducing the cost, as you only pay when you put some workloads to the application. And at the same time, it's also scalable. Like the moment users submit some jobs, ML processing jobs, that moment it should immediately start also, right? So here is an overview of the whole application architecture. It starts with uploading the new STL file. So user will upload STL file which needs to be predicted, and at the end we see that result or output of obj file is created, and that is now converted into a 3D viewable file which will be visible in the UI of the application. So here we have some screen capture of the application. This is the real application which is hosted live currently. Now we see that the user is uploading some STL files on the left hand side, and the results or the predicted results of the STL model is being displayed on the right hand side. So usually the process would take somewhere around 30 seconds to 1 to 2 minutes. So I will browse through a few more examples. You can see it is not fully accurate, but that's how the machine learning nature is. It does very good predictions in most of the areas, and there are some more improvements that still can be done. So we can spend some time in looking at the color coding. Like here you can see planar color is brown, so brown color is mostly visible in the planar sides. These ones, they look flat, but they are not. They are cylindrical in nature, and yellow is for cylinder. So it's difficult to visualize these surfaces as cylinder from our eye, human eye, but that's the power of ML model. And the ones that are cylinder in nature, which are visible to us also, we can see that those are also colored in yellow. All right. So we'll now move to the another segment of our webinar. Here this is a slightly different use case, but it's again falling in the same autonomous geometry processing area. The second objective that we will discuss now is about detecting 3D objects, detecting objects from 3D space. So the use case is like this. You have a 3D model. Let's say this is like, for example, this model is of a room which contains a table and 4 chairs. So our objective is to take this 3D model file and detect that this model contains 4 chairs and a table. So that's the problem statement, and let's see how AI can be applied to do so. So this use case is pretty similar to the object detection that is done in images today. So nowadays we know that the object detection in images is extremely robust, and this is one of the example where we are able to see that all the various aspects of this image is being highlighted properly. So humans, persons, vehicles, signboards, etc. So similarly, when given a 3D object, can we also do the same? So our approach here was pretty much simple and pretty straightforward, like the one we saw in the image classification example in the last slide. So what we do is we take a 3D model and we take a snapshot of the 3D model, and that becomes a 2D image. Then you pass it to the image detection layer, and once you get the bounding boxes of each of the objects and mapping those bounding boxes and identifying the 3D objects which are in the 3D space as tables and chairs. So downscale to 2D, do the image processing, and then upscale again into the 3D. So this is how it works. Autodesk Forge Viewer is used to load the 3D model into the viewer, and then a snapshot is taken of the 3D model. This snapshot is passed on to the AI layer, which will detect the objects. Once the objects are detected, we then translate or map the 3D objects which are present at those locations. So that's how this second use case was also addressed. Again, in order to create this application, we will need to create a full-fledged web application, right? So some of the architectural diagrams and all which was used to create this application. The interesting part that we did here is we were able to run or automate the browser inside serverless services on the cloud, so that this Forge viewer could be used in capturing images of or rendering 3D in a serverless environment. Running rendering images of 3D models on a cloud environment in an automatic fashion. So Google and other cloud services also provide these ML services, which really helps us to reduce the development time of our AI applications. So that's how the full architecture is here. So I'll just quickly read this. Upload the new CAD model. So here it starts by uploading the original CAD model, and then the Google services is consumed internally to get the detection, and then finally the objects are renamed, and user gets those objects with their proper naming as they have been detected. So that's how this whole architecture works. Here we can see an example or snapshot of the architecture. Tables and chairs that we can see here, they are also highlighted here, chairs. So we are currently showing a list of chairs, and it says that there are 14 chairs. So AI was able to detect and then count them. So cool, isn't it? So I guess that brings us to the end of the technical content of this webinar. I would suggest all of you to visit our website, visit our experiments website. It contains a lot more presentations and demonstrations of technologies that we have built. Do write us at info@cctech.co.in.
Okay, so I'll quickly give a demonstration of this application in a minute.
If you have any questions, please write into the chat window so that we can also answer them. Looks like we don't have too much of time for Q&A, but we will take up as many as possible.
Yes, so this is the experiments website that we have, and we'll quickly move to our application. So here, yeah, this is a dashboard which shows the previously used projects, previously conducted projects, and let me quickly go to one of the completed projects. It's a demonstration of how the user is uploading a file, the detection process is happening, and then the raw geometry is being displayed on the left hand side, and can see without any, the raw geometry did not contain any patches or any information about the curvature, but the ML model was able to predict them. It's not too accurate, but yes, it's able to detect more than 95% of the surfaces accurately. Right. This result can then be also downloaded as a zip file. This will contain the separate OBJ files for each of the patches. And also, we can go and upload new geometries and test our application. So for your own projects, you CAD models, you can try this application. So it would take a minute or two, if I go ahead and do this. So I'll just close the demonstration here and invite all of you to please take advantage of this service and to test your geometries.
Okay, so I think there are some questions have started to come up. Let me go one by one. Sonali Patil has asked, can we use this AI model to read geometry from G-code file? So I think Sonali, G-code file are meant for CNC data, and CNC file does not have a geometry as such. So if you have some other file format in mind, please let me know. But on a broad level, we are working on a mesh file format, and STL and OBJ are pretty standard. And if you have any other format in mesh, you can always convert into STL. So the base right now we are stick to STL because that's one of the most popular file format there. The next question is by Anil. Surface detection can also provide the parametric information such as curvature and concavity. It can be. Right now, the objective was limited to the surface segmentation or detecting a surface type. We had done some work with some other client, and where they were looking to also find out a manufacturing feature. So where this set of features become a base thing, and then we able to detect that the whole thing is forming a hole or that forming a protrusions and things like that. So we can build basically a model which takes this as an input and then produce certain thing. Curvature, so property wise may not be the thing that's possible because ML is not that great in that sort of thing, but it is very good in deciding one way or other. So I would say that's the next question. Nandeep Mamre has a question. More the features we have, more will accuracy of model and prediction. Do we have some thoughts on automatic feature generation or better training on the model? Would you like to take this, Subhanshu?
Yes. Okay. So very interesting question.
I think we have a reverse experience on this. Yeah.
Yes, so that's true. Automatic feature generation will it's the standard way that ML these days are happening. So yes, that's true that it can work. But yes, even after that, there needs to be a human engineer to curate that information and then understand or clean the data and enrich the data. So it needs some intervention. But yes, the exploration of the data set and the feature set is definitely a strong supporting point for ML model.
One of the things to add Nandeep's question, that one of the things that we did was we started with around 150 features, and then we started to also curate what are the features that are not contributing to the whole the final model, and we reduce the number of features. So I think that's a continuous process. You keep on looking for a new feature that provides the insight to the ML. You look at it, you do analysis, and then you come back. So it's an iterative process. Automatic feature recognition for so feature generation for this is I think interesting approach. So Let's see if there is something that is there in literature that we can refer. Okay, so yeah, looks like those are the all questions. Any other questions?
Okay, I guess there was one that was directed to me, so that might be the reason Sandeep you did not
Okay.
get it. So I will read it here. So Digvijay is saying that sorry I joined a bit late, but curious to know exactly what problem are we trying to solve using this? What would be the obvious next step after geometry?
Okay. There are a lot of application for this to use this technology. Say let's say you have certain workflows in your industry, whether you are AEC or you are manufacturing, and you are working with a data which is a mesh data. Then most probably you have a set of engineers or designer who is basically converting that mesh data or that point cloud data into certain parametric data, and then thereafter you start to work. So that's the one of the thing that we are targeting. So we have our own application for CFD simulation, and in that we wanted to support also STL file. When we bring the STL file, there is no way to tag certain surfaces. So because in a CFD you need to know the inlet surface, outlet surface. So this is the application that helped us. So we have integrated that into our own product. That's one of the things. But I see a lot of application in CAM. Let's say you want to work on is a CAM toolpath generation on mesh data. Then again you need certain features to be known. You want to work with process planning, you again need to know this information. So there are a lot of application areas for this. There's one question from Vikas. Although question could be off the track, but if I'm not wrong, the mesh morphing first thing need is segmentation, which is addressed here. But is there any way to extend it to mesh morphing too? So Vikas, did you mean UV morphing kind of thing? So yes, actually, if you're looking to do something like a UV mapping, what we call as a mesh morphing, I think so. It's the same thing, texture mapping kind of stuff. So if that is your thing, then it is possible to use this technique to do segmentation and also to generate that. And I think I saw in one of the software they have kind of auto morphing kind of thing, and might be they're doing it machine learning or something. Our idea was not to go towards mesh morphing or things. Our idea is like to go towards higher level of features. So able to detect, let's say uh, if it's a building data, then can we use this to for point cloud kind of thing, scan point cloud and then able to detect objects such as windows, door, existing building that you scan through, if there is a piping, ducting, that able to detect, and also be able to do it not just to detect the object, but able to create a parametric model out of it. So in that sense, we realize knowing the surfaces would be a lot more important, and that's the way we started targeting towards it. Thank you. Subhranshu, I think we have reached to the end of the
Yes.
time. So thank you all for joining today's webinar and going through patiently. It was a little bit too much technical in a sense, but there was a lot of material to cover. Might be next one will be more focus on practical application of this technology. Keep connected to our company channels. We will be also writing a follow-up blogs on some of the questions asked in both the sessions and giving some more information and some more insights on this project. Thank you.
Yes. Thank you, everyone.
Good day, good night.